A common technique to evaluate antiderivatives is u-substitution. So suppose we have an antiderivative of some function f, which is a composite function of u of x. Well, using the chain rule, we can differentiate the antiderivative with respect to x. So what we get is the derivative of the antiderivative with respect to u, which is f of u, and du dx is u dash of x. And now if we separate dx and then integrate both sides of the equation, then what we get is the antiderivative as a function of x. And we can write this in another form. So du dx is du. And this is the form where we can apply u-substitution. So from this expression, u-substitution works where we have the function of u multiplied by the derivative of u. And we'll see that in several examples. We've seen that u-substitution can be applied to indefinite integrals, where we're integrating a composite function of u multiplied by the derivative of u. And this basically gives us the antiderivative by reversing the application of the chain rule. Now where we have a definite integral, and we're integrating with respect to x, we're going to integrate from some x equals a to another x equals b. So when we apply u-substitution to a definite integral, we need to change the limits of integration. And remember that u is a function of x, so we instead integrate from u of a to u of b. And this will become more clear when we look at example problems. Let's evaluate this integral. So we can see that we cannot apply u-substitution, so we'll simplify the integral algebraically by multiplying by e to the minus x on e to the minus x. So if we take 5 outside the integral because it's a constant, we have e to the minus x over e to the 0, which is 1, plus 8e to the negative x. And this is evaluated with respect to x. And now we can use u-substitution. So if we let u equal 1 plus 8e to the negative x, then du is equal to minus 8e to the minus x dx. And therefore we can rewrite this integral as 5 by the integral of e to the minus x dx, which is minus du on 8, and that's divided by u. So evaluating this integral, we get minus 5/8 by the natural log of u, which is 1 plus 8e to the negative x plus the constant of integration. Let's evaluate this integral. So you may recognize that the derivative of tan x is sec squared x. So if we let u equal tan x, then du is sec squared x dx. And therefore this integral becomes the integral of tan x, which is u, by sec squared x dx, which is du. And therefore this evaluates the u squared on 2, so it'll be 1/2 u squared, where u is tan x, so we get tan squared x, plus the constant of integration. Let's evaluate this integral. So this time these terms are not derivatives of each other, so we can write this as the integral of 1 over cosine pi x, and tan x is sine pi x on cosine pi x. So now we can set u equal cosine pi x, then du is equal to minus pi sine pi x dx. And therefore we can rewrite this integral as sine pi x dx, which is minus 1 on pi du, and u equals cosine x. So what we have is cosine x squared, so therefore we can write u squared. And evaluating this integral, we have u to the minus 2, so we have minus 1 on pi by u to the minus 1 on minus 1 plus the constant of integration, and therefore we end up with 1 over pi by 1 on u, or 1 on cosine pi x, which is the same thing as sec pi x, plus the constant of integration. Let's evaluate this integral, so we can try to manipulate it to apply u-substitution. So cosec squared 2x is 1 over sine squared 2x, and we can multiply this by 1 over cosine squared 2x on 1 over cosine squared 2x, and we integrate with respect to x. So we can rewrite this as sec squared 2x in a numerator, and in a denominator we have tan squared 2x integrated over x, and now we can use u substitution. So u is equal to tan 2x, and therefore du is 2 sec squared 2x dx. And we can substitute for this term in a numerator, so that gives the integral of du on 2, and in the denominator we have u squared. So integrating u to the minus 2 gives you u to the minus 1 on minus 1. So what we get is minus 1 half by 1 on u, which is 1 on tan 2x, or the cotangent of 2x plus c. Let's evaluate the derivative of the cotangent of x. So using trig identities, we can write this as a cosine on the sine of x, integrated with respect to x, and then using u substitution, we can let u equal sine x, and then du is cosine x dx. And therefore we can write this as the integral of du on u, which is a natural log of u, where u is sine x, plus the constant of integration. Let's evaluate the integral of 1 over x by the natural log of x. Well, we can let u equal the natural log of x, then du is equal to 1 on x dx. And therefore we can write this as the integral of du on u, which is equal to the natural log of u plus the constant of integration, where u is the natural log of x. Let's evaluate this integral. So we can let u equal cosine x, then du is minus sine x dx. And therefore we can write the integral as the integral of 5 to the u with respect to u, but we have a minus there. And therefore this evaluates to minus 1 over the natural log of 5 by 5 to the u, which is 5 to the cosine x plus the constant of integration. Let's evaluate this integral. So we can write this as the integral of x squared over 1 plus x cubed all squared. And now we can set u equal to x cubed, then du is 3x squared dx. And now we can write this integral as 1/3 du over 1 plus u squared. And that's equal to 1/3, and you may recognize this as arctan u. And u is equal to x cubed plus the constant of integration. Let's evaluate this integral. So we can write this as the integral with respect to x, and in a denominator we can factor out 16, So we have 1 minus x on 4 squared. And therefore we have 1/4 by the integral with respect to x on the square root of 1 minus x on 4 squared. And if we let u equal x on 4, then du is 1 on 4 dx. And therefore what we end up with is 1/4 by 4, which is the integral of du over the square root of 1 minus u squared. And you may recognize this as the arcsine of u, so we get the arcsine of x on 4 plus the constant of integration.